Okay, so welcome back. Let me see if this board lighting. I don't know if that because it's pretty bright, but let me play around here with whichever one of these. Okay, that's maybe a little better. A couple of announcements. So the muddiest point for this week is due on Sunday. Again, not looking for much there. It's just a little Canvas assignment, sort of one sentence or a few words for each line, kind of like what was clearest from this week, what was muddiest. Try not to, if everything was clear to you, it's tempting to say everything made sense to me. But I want you to kind of order things in your head to like say what made the least sense of all the things that made sense and tell me that. So then kind of be ranking on that. So like I got this, but it took me a little longer to understand that. You don't have to tell me why, just sort of interested. It's kind of a survey of, what were the easiest things for you to get? What are the more complex things for you to get? There is this concept check, which is this unit is broken up into two concept checks. And so there's one of them that will be due not this weekend, but next weekend, at least tentatively. That might be pushed by a couple of days for a reason I'll explain here in a second, but that's something else to look for. And then the second one will be due a little bit like, say, right now, I think it's scheduled for February 9th. These, again, concept checks. They by default we drop your lowest three. So and there's 8 units, so roughly 9 or 10 concept checks. So that's how to consider how you would balance your time with those. But a week from today, so Thursday, I have to go to a PI meeting in DC. So I'll be on Tuesday. I'll be here with a suitcase, and I'll have to head to the airport right after this, and I'll be back Thursday night. But that means I have to miss class Thursday. So instead, I am going and putting together a perusal reading discussion over a small chapter on the GA that I'm going to add as a concept check, and I'm going to then make it so that it'll drop 4 instead of 3. So basically, in lieu of the time you'd spend on lecture, I'm giving you a reading assessment. And if you've never used perusal before, it is a tool that is kind of merges discussion and commenting and annotating with reading. So you read an entry, and then as you're reading, you make annotations, and it uses AI to sort of to judge how in depth your annotations are, and it scores heavily on your interactions with other students. And so someone else says, "Oh, this is a difficult concept for me," or "I didn't really understand that," and someone responds. If people respond to your comments or you respond to other comments, then that actually gets very high weight in its scoring. And then I might add bolt on a couple of questions at the end to just sort of quiz questions that will eat up some of those other points, and then it'll sort of give a score. And that will then just, again, contribute to the concept thing. So I think that really will reinforce the topics that we do in lecture. And then I'll just come back on track then the day or the Tuesday after that. So um, no class a week from today. There will be class Tuesday, though, and instead there'll be this perusal assignment that I should wrap up hopefully today and put online. And you can use the time that you would spend during class to wrap that thing up. And again, I think it'll be a similar thing. So I apologize that I have to do that, but it's just something I couldn't get out of in the timing. I thought it might work that I could miss the class, but there was no way I could get flights to make it work that to get to be back by Thursday. Okay, so any questions about administrative stuff? All right, great. So we left off last time talking about heuristics, and so now we're going to try to ground that a little bit more in um, engineering design optimization. So so that's just the top heading here. Otherwise known as EDO. And so engineering design optimization is a way of couching complex engineering problems with multiple variables and potentially multiple objectives that you're trying to reach into a mathematical framework that can be explored in with computational tools. So the In an optimization context, you can imagine generically, let's say I have the problem minimize some function f that takes a vector of parameters, um, or equivalently, you could be maximizing minus f. So you have some design objectives, and I'll get examples of that in a second here, but like minimizing a loss function is one example. That has a bunch of different variables here. So I should say that I should be specific that, such that this vector x is in some set big X, which is a subset of, let's say, Rn, where n is, greater than or equal to 1. So the idea here is I've got a bunch of different parameters that I would like to pick. There could be hundreds of them, there could be thousands of them, there could just be one of them. And they could be constrained where not all possible values. And they could be constrained in complex ways. Like it might be that parameter one plus parameter two has to equal a certain number. And so as I choose parameter one, I'm effectively also choosing parameter two. Or it might be that parameter one plus parameter two must be less than a certain number. So I only have a certain amount of money, and I have to, in dividing my budget between different bins that I'm spending on, but I only have a certain amount. And so it might be that X1, which is how much money I'm spending on asset one, and X2 is how much money I'm spending on asset two. Those two have to add to a number that is less than my budget. So there can be complex constraints, which we capture by this subset. But the important thing is just a multivariable problem, and I've got some objectives that I are arbitrarily saying I'm going to minimize. But if I want to maximize, I just put a minus in front of that, and it's the same problem. So this can solve any kind of single objective problem. And so, so what are examples of F? So, where F might be. So some examples could be like, you know, well, sorry. So F, I guess I'll say F is. Well, okay, I'll do might be, so I don't have to erase things. So generic. So what are properties of F that make this a hard problem? Well, F could be very costly to compute. And so what do we mean by costly to compute? Well, that could mean, for example, that I have to actually run, and maybe I'll give examples down here. That might mean that I actually have to run a real world experiment every time I want to evaluate F. So, as an example, some of my friends in evolutionary robotics, they actually will have a bunch of robots and a control loop where they can download parameters into their robot, actually watch the robots do a task in the real world with cameras and everything like that, evaluate how well things did. That comes a back into a system that has the ability to update those parameters, and they can evaluate, well, based on how well those robots did in the real world, then I might move the parameters in one way or another to see if I can get them to do better. And so that's an example. It's extremely costly because that experiment might take 10, 20, 30 minutes to run just to evaluate one particular X. So that's one example. It could be a real world experiment, or it could be a simulation. So some of the work I do is we're choosing wetlands in across Texas that balance the objectives of flooding as well as storage during droughts. In a wide variety of places all throughout Texas. So if you have a fixed budget for what wetlands you can enhance, then where do you choose to put those, given that you have all these multiple objectives that I want to make sure this place has enough water, this place doesn't have too much water, and so on and so forth. the sims that I have to run every time we come up with a new set of wetlands take on an order of 10 minutes to run. But there are something like 1,000 wetlands that I can choose from. So if you think about the power set of that, that's like 2 to the 1,000 options. That's more, atoms that there are in the universe that I could possibly go, two to the 1,000 different configuration of wetlands throughout Texas. I can't do them all. I have to step through them. And for each one of them, the sim that evaluates how well that configuration ran takes about 10 minutes. So on a fairly sophisticated machine, maybe 5 minutes on an even more sophisticated machine. So it takes a lot of time to evaluate how well that particular variable did, let alone to evaluate lots of them and then choose the best. And then, so that's another way it could be costly, or it could just be numerically, a costly numerical operation. So, for example, integration. So there are a wide variety of engineering problems where the optimization objective is an integral. And these can come down to inference problems as well. Like you might be trying to figure out, let's say you're doing a Bayesian inference, and so you don't actually care about a single point estimate of a parameter. You want a probability distribution. And so you want to say, what's the best distribute based on these data? What is the distribution of parameters that could have produced these data? And so you want a curve that comes out of that and a posterior probability. So you had like, well, they could have been, uniform, but then I put these data in and then it pops out some complicated posterior that actually better reflects the data. And so how do you get from the uniform to that? That's a complicated process that in order to form a probability distribution, it's really important for the probability distribution's area underneath it to be one. And so you can't spit out a probability distribution without normalizing for that distribution. And so you need this complicated integral. And so it can be really costly to do numerical Bayesian inference. So that's another example. And then other integrals. There's a bunch of mechanical properties that require you to integrate under the curve in order to even calculate. And integration can get very ugly, requires a lot of approximations and so on and so forth. And so this, can do this. So there, just in general, there's a lot of reasons why it seems like once you've formulated things here, it should be a simple problem, but it's not easy to calculate this thing all the time. So that's one of the key problems in engineering design optimization. So what are some examples of F? Also, that might be relevant to some of you. So I've already given a few, so I said, simulation model. Um, so let's say a high fidelity simulation model. We'll say high fidelity of a physical process. A lot of the multi-robot work that we do in my lab and adjacent labs is we have multiple scales of simulation where, we have the simple one where it's a bunch of dots moving around on a screen, and we can run lots and lots and lots of replications of that to see how well a team works out. But ultimately, before we implement it, say in the drone studio with lots and lots of real robots, we have to then get some validation that our little dots that worked in 2D aren't going to fall out of the sky when we actually put them in 3D on flying drones. And so we need to gradually crank up to higher levels of fidelity where we eventually do get a simulation where these things are flying in 3D. But now they've got real physical forces, there's might be wind gusts and other things like that that we want to sort of simulate to see that, okay, well, when we add all of these actual physical reality into it, things still work roughly like they did in the high fidelity or in the low fidelity one. But the downside is, whereas we could run a bunch of reps of the low fidelity one with huge speed ups, so relative to real time, 1,000 speed ups relative to real time, the The high fidelity simulation might only be able to run in real time, in which case I may as well, for time purposes, just be running it with the real robots. It's safer to run it in the sim, but I don't get any speed up for running it in the sim. Some sims might be slower than real time, if it's a really, really complex system. So you can be very costly if you have to do these sims. And like I said, mathematical expression with no closed form. So, what do I mean by with no closed form? That means that, it depending on the values of the inputs going in, you might have to use a totally different expression. You might need to use some sort of approximation, and so on and so forth. And so that can be an issue. Like I said, it could actually be a real physical system in the loop of your optimization process. Um, And this is sort of an interesting thing is that sometimes when we have real physical systems, then you you want some surrogate that so you don't have to actually go out and do the real system. So this could also be a surrogate for a physical system, like a neural network. This lag is, it'll eventually erase. Starting to, there we go. So what do I mean by that? So in this case, like I've worked on problems where the we had to know whenever you sent a certain amount of power to lights in a building or heaters in a building, then they would produce patterns of actuation. It would produce lights on tables or lights on the floor or heat in the buildings and so on. Well, if you wanted to explore different ways to do decentralized energy allocation around the building, then you could go into a building because it's a complex thing. Nobody may actually have a model of that built. So you could go into the building and say, all right, well, I'm going to just implement my controller and I'm just going to have it try things and then see what happens. Or you can go through a commissioning process where you can roll a cart through the building and have it collect data. So for different inputs, what are the outputs I'm getting? And then it then can train a neural network model to be an approximation of the building. So then I can say, as long as I put these inputs in, the neural network's going to predict where the light is going to be in the building, where the heat is going to be in the building, and so on. So then my neural network becomes a surrogate for that. But it might, be a very complex neural network, which itself takes a little while to crank through if it's a very, it has a lot of things here. So in here, I'm not actually optimizing the neural network. I'm using the neural network as my optimization objective. So here, this is the ANN is the objective. So, otherwise the ANN is F. And in this case, the inputs are the inputs. So the inputs to the ANN are the inputs to F. This is in contrast to another option where the F could be a loss function for an ANN, where here it is flipped around here, where the inputs are the weights and F is then the actual loss. And so, what do I mean by that is like, if I'm actually doing the training, then I'd like to minimize the difference between my approximation and my real system. That's the loss function. I like to minimize the loss, but here the inputs are the weights. And so sometimes neural networks are actually the optimization objectives themselves. Sometimes neural networks are the things being optimized. So and this is, and we talked about last time that we can view a neural network as a type of heuristic, where the weights are parameters. And really, I should say up here that, my X hat, these are the parameters that I'm optimizing. All right, so those are examples of what we might do in an engineering design optimization. Questions? The loss function down here, so we can say that F um, can be a loss function for a neural network. So the idea would be that I have a neural net, and again, we'll talk about neural networks later on in the semester and where they come from. But a neural network is just a complicated regression problem. It's a a neural network. So if I want to say, what is A and N, we your neural network. If F is my neural network, then it basically is a black box which has inputs that are combined together with weights, combine inputs in different ways in an effort to make an inference. And so the example might be that if I happen to notice that let's say my inputs are this could be power to each of 100 lights in a cubicle farm. And this up here could be the actual illumination on 50 desks in cubicle farm. So I would like to know if I turn on these 100 lights in this particular pattern, some of them are 100%, some are 50%, some are 20%. If I'd like to do these different patterns here, then which desks are actually going to get illuminated? Some desks are fed by 3 of these lights. Some desks are fed by 1 of these lights. Some desks are fed by 15 of these lights. So all of these different lights get combined. So you have some set of lights combine to illuminate each desk. And so you've got this is happening times 50. So each desk has got a different set of lights illuminating it in a different way. And so I might would I have a real system that's doing this, and this is my approximation of a real building. So so what you do when you train a neural network is you want to make this approximation as close to the real building as possible. So what you would do is give the same inputs. You'd say, okay, I have data on this building. When I light up these lights, these desks have this illumination on them. I put sensors on all the desks, and I know how much power I'm giving each lights, and that's a data point. And then I'll do the same thing. So I'll light up a bunch of other desks or light up a bunch of other lights. I see which desks are there. So I might have 100 or 1,000 data points of different ways I could light up these lights. And for each one of them, I get different illumination patterns on these desks. And so then I take those in and I say, I'm going to form a loss function. So my loss function here might be it is going to be so I'll call y minus y hat. And I will then take the 2 norm of that. So this is just um, sum of squared errors between real desk illumination and approximate desk illumination. And so the real desk illumination we're going to call that's this y, and then the approximate is this y hat. So this is like, y one, I'll say this is like component. Yeah. So this is like y1 minus y hat 1 squared plus y2 minus y hat 2 squared plus where this is like illumination difference on desk 1. This is illumination difference on desk 2, and so on, all the way up to the 50th desk. And we're going to call this our loss function L. And so if we've done a good job creating the weights, how these different combinations, combine in our neural network, then when we put in a certain power pattern that actually existed in the real world, we'll get a very similar power pattern in the neural network. Initially, this will be way off, but so we feed this in. So this here, this L, this loss function, this is our F in our generic problem. This is, we want to minimize a loss. And if we do that, then we'll create a neural network that for power distributions we have not tried, it will then hopefully accurately predict what would go on in a hypothetical building if we did try them there. And so our goal here to create that surrogate was to minimize that loss function, and then assuming that it'll generalize. Does that answer your question? Any other questions? And then I meant to mention this last time, but part of the reason why we it's variable how long the units last is I really do encourage, and I think we'll get more opportunity for it as we go on, but I do encourage, if there are questions or comments or extensions, then feel free to bring them up. I want this to kind of be open-ended, which is another reason why I don't just have slides here, so that we can kind of take this in different directions. Okay, so that's the general idea behind EDO, complex optimization objectives. If you can manage to optimize the optimization objective, you create a so-called design for an engineering problem. So, how do we solve this generic problem? This generic problem of minimize F such that X is in your this space. So how to solve? Well, how would a high schooler solve this problem? So this is an optimization problem. How are we taught to solve optimization problems? Any thoughts? What's the first thing you look for when you try to solve an optimization problem? Yeah. Yeah, where the derivative is zero. So, or just generally, it would be nice to know the gradient information. So I'd like to know, use the derivative. Or in a little fancier speak, use the gradient. Where the gradient is just the direction of steepest ascent or descent. I'm going to say ascent, but and then you can build a gradient descent algorithm. And so, a gradient is just sort of a multivariable derivative. And so ideally, if the gradient, which I'll then call um, del F, is available, great. Then we can use conventional methods like, Newton's method. And so that's basically, if you've got a function that looks something like this, and you start somewhere here, then you can basically use projections of the gradient to say, well, if I'm doing a minimization problem, then I am going to go in the direction that the gradient is telling me is downhill. And so I'm just going to then create a little step, and I will then maybe move a little bit downhill. So Newton's method basically says move in a step downhill and try again, over and over and over again. And this isn't something that we're going to go over in this class. This is just the kind of typical way that if you had gradient information available, then great. You can just use something like Newton's method, and then, the more elaborate versions of this, like stochastic um, gradient descent, which has become very popular for neural networks because a a wide variety, a huge family of artificial neural networks have been crafted with this convenient property that their loss functions are differentiable. So they have gradients. So that means that these high school level methods are available to them. And so most neural networks that are trained with things that, people have been doing for, 200 years. And it seems to be working pretty well for those. But this isn't always the case. You don't always have gradient available. So that ends up being kind of the more interesting case for the generic engineering design problem. You don't have a gradient available if you have a physical system. You don't know necessarily the rate of changes. You might be able to approximate it, but is that approximation any good? That's when we're starting to get into these other methods. So that brings us to a so-called direct search methods, which I'll abbreviate sometimes as DS. And so direct search methods, these explore F without, we'll spell it out, theoretically. And so how do they do that? So there are a bunch of non-nature inspired ways. So one of the oldest ways to do this, I don't want to say the oldest, but I'll say one of the oldest, is so-called tabu search, sometimes abbreviated TS. And so tabu search is a so-called local search or neighborhood search, which just means that you started off somewhere in your parameter space and it makes small steps nearby. And that's how it explores the parameter space. And so it explores locally, and as opposed to making giant jumps around the space. And so how does tabu search do that? Then it basically, you say for current X, we're just going to make a movement, and that is a nearby movement. and we can move to a worse solution to explore, so long as it is new. Um, but what's taboo is moving to solutions that we've already tried before. So we are going to, for current X, move nearby, and a solution nearby may be worse, may be better or worse. And we're going to keep track of currently what is, so keep track of best. But then never revisit the same configuration twice, or never revisit the same configuration. I'll just say that. This is where the name taboo comes. So it is taboo to go back to that. I already tried x1 equal 5, x2 equals 6, x3 equal 4. So 5, 6, 4 is a spot that I can never come back to. That's taboo. I'm going to remember what it is. And then so this is a way of just keeping track of your progress and kind of moving it around. And in taboo, there's not a lot of intelligence there. It's just gradually searching through a space and memorizing the space and keeping track of what's best, and just making sure that you don't ever duplicate your efforts. That's taboo search. So that's an example there. Clearly, there could be room for more intelligence, but it's surprising how well taboo search works for a lot of optimization objectives, especially if you intelligently initialize them. So if you have a rough idea that the solution is somewhere in this area, maybe another heuristic led you there, then taboo search can help you kind of find a better position around there. So that's another reason why these local searches, we might use, often use local searches for fine tuning. Because in these design problems, we often have hybrid optimizers where optimization approaches where we use some coarse grain method to get us in the neighborhood, and then once we're in the neighborhood, switch to a fine grain method to try to optimize within that neighborhood. So that's an example of taboo search. All right, that's not nature inspired at all. That's just kind of, I think, sort of straightforward. Any questions so far? Yeah. Great question. So yeah, I think that's going to depend for a discrete optimization problem. So I guess I should mention that X here could be continuous or discrete. So in the discrete case, then it might just be there is a clear topology of well, that's the next option. I can easily step over. But when the problem is when it comes to continuous, then you need sort of a step size, and you kind of that becomes a parameter, a hyperparameter of the taboo search. But so one thing you may have to do before you do your taboo search is discretize your space. And then once you discretize your space, then now you have tiles on the floor. And if I'm stepping on this tile, then it's very clear that all my neighborhoods are these tiles around me. And so then I'm stepping to the center of that one. But then, is it a good discretization, which is effectively, is it a good step size? And then that becomes another thing you have to optimize. Any other question? Yeah. Oh, right, right. It's a great question. So when to stop? Or otherwise, when have we reached convergence? Um, for all of these heuristics, there's no guaranteed way to know that you're there unless you manage to search the entire space. But if you manage to search the entire space, it doesn't really matter how you did it. You had enough time, you may as well just enumerate it in your favorite way and then go through the entire enumeration, do brute force. So you'll never know that you actually reached that, but you can get some confidence. For example, if I've never seen a better solution in 1,000 steps, okay, that's probably good enough. In 100 steps, in 10 steps, that becomes another hyperparameter that you get to set. So you just have to try it. You find that for certain optimization objectives that are well behaved, then your convergence conditions may be very different than other optimization objectives that are sort of ornery, that have a lot more pits and pockets and things like that. Yeah, and that's something I guess I should have mentioned about this F function. That probably would have been a good thing to add in here. So when I said it can be costly to compute, um, I think I got excited about examples, but I meant to also say that it can also have, and I'm sorry for going back, but has many local optima. So as an example, it might look like this, where this is a local optima, this is a local, this is a local, this is a local, this is a local, but only this is the global. And then it also, I did say this, but is a function of many variables. But this has many local optima. That's where, there's a speed accuracy trade-off here, where your taboo search may be really excited about this one, but eventually, because of the taboo property, it will eventually march and find this one and this one and this one, and eventually it will find this one. So if you give it enough time, it will eventually find this one, which is slightly lower than this one. But if you happen to start it in this valley, then it's going to be very excited about this one, and it's going to seem like this one, which is very far from this over here, because it's going to take a local search a long time to get over there. So, that's a balance you have to do. Okay. So that is taboo search. All right. But there are a bunch of other search approaches that we can take. All right. Any other questions about these direct search methods? Yep. Well, it's easier for me to do with one parameter, but no, you can do this with multiple parameters. So if again, you're probably gonna have to discretize the space before you start a taboo search algorithm. That discretization can be in multiple dimensions, and you can define a local neighborhood as as the cubes, and I go from tiles to voxels, I guess, the voxels that are immediately adjacent to your voxel, but that can be in multiple dimensions. And so as long as they're pushed up against an edge of you in multi-dimensional space, that is an admissible step. Does that make sense? Yeah. Yeah, it's a brute force with memory. It's a brute force that prioritizes the search locally and has memory so that it doesn't accidentally go back and redo the same thing. It can. I mean, because of the taboo, it never will go back to its previous one. So it could, as it steps over here, it's never going to step back. So it will eventually diffuse its way through the whole space. Or you could say, especially if it's discrete, I would say, yeah, I think it is going to eventually diffuse through the whole space, but it's going to take a very long amount of time. So it's just a way to prioritize, coming up with its own enumeration of the space. So that's why these local search algorithms are really best when you have high evidence that you're very close to a good optimizer, but you just can't find it yet. So then you switch over to a local search, you initialize it in that neighborhood, and then hopefully it finds that, it fine tunes. So I would not say, if you know you've got a really well-behaved optimization objective, you just don't know quite where the bottom is, and it's just too ugly for you to solve using other methods, you can do this. Or if you've got a really ugly optimization objective and you've had some other method get you in the neighborhood, but it's too excited to fine tune, then you could switch over to something like this, and then it will kind of exhaustively look through that neighborhood. Okay. Other questions? Good. I'm just going to calibrate. My watch didn't charge last night. Okay, so there are other methods, and many of them are nature inspired, and they roughly fall into these two major categories. And so the first category are trajectory methods, which are very much like taboo search, but maybe with a little bit more intelligence. And so I'll call these local search based metaheuristics. And this is like taboo search. And then there are our population-based methods. And I guess I should like taboo search, but I'm also going to mention simulated annealing, which we will focus on specifically a little bit later in the course. So this is just a preview. So later in course. So simulated annealing is a meta-heuristic that falls into this category, but is inspired by the way in which physical systems cool. And so you sort of heat up your artificial system and then let it cool down. And if you heat it up enough just right and let it cool down, then it will cool into a hopefully optimal configuration, even though it started out in a suboptimal configuration. So that's what we'll talk about then. But before we get there, we're going to talk about these population-based methods. And so these are like the genetic algorithm, which I'll abbreviate GA. Um, there are also ones like ant colony optimization, which I'll abbreviate ACO, which we'll talk about later um, as well. And then there are some weird ones that like harmony search, which we won't talk about, but is one of the options that's available for you to investigate for your final project, and particle swarm optimization, which we will talk about, which I'll call PSO and others. And so what is the defining feature of these? Now, you could also divide these into, could also further divide by memory. So you can have, like, taboo search has memory, it remembers where it went. Simulated annealing does not have memory. It doesn't remember all the places it previously went. So if you continue to run simulated annealing, it's possible that it can go back to previous versions. Now, there is a technique that we use in optimization, something's called memoization, which is the idea that if I do happen to go back to a spot that I've visited before, I don't necessarily reevaluate the optimization objective. I just pretend like I evaluate the optimization objective, and then I use whatever stored value is there. So it's sort of a way to kind of mimic this taboo-like idea. So this isn't so important for this class, but you will notice as we go and like, oh, well, this one makes use of memory in order to achieve this function. This one achieves that function without memory. So it is possible to further divide these by whether they have memory or not. All right, so what do these basic structures look like for these? So a basic direct search structure, regardless if it's taboo search or whatever else, is pretty simple. It's you have some initial X, which you then use it to evaluate um, F of X. So this could be simulation, um, real, whatever. And then from there, that gives you a an F that you pipe into some output metric. So there's going to be some evaluation, which so you evaluate F, it returns F, and then you sort of have to evaluate, is that a good F or not? So I'll just put that as some metric, which I'll be using to evaluate whether um, F is good or not. And from there, then you pipe that into your optimization algorithm. And that could be tabu search, that could be the GA or whatever. And then that optimization algorithm is going to, as brought up, figure out, have we reached termination? Sorry, that's supposed to be termination. Let me see, let me clean that up for you. A little bigger diamond. So termination conditions met. And if so, then, so if yes, the termination, then we present our results. So this is where you get your X out as a solution. I'll call it X star hat. So this is our output. Otherwise, if not, so this is no, then we have some sort of way to propose new solution and restart the process. So pretty straightforward. This is all your direct search, regardless of their population-based methods or otherwise. They're pretty much going to work this way. Now, for termination conditions, this has already been brought up. This could be based on convergence, like I said, but it also can be based on budget. So we already mentioned convergence, but it also could be computation budget or some other sort of, so I'll just say budget. And this is usually in terms of, say, computation. So if you have all of the computational time in the world, then you'd let this thing churn until it's been a really long time since you got a new result that was better than the previous result. But it might be that you're limited, so you only budgeted an hour on Sol to run your optimization algorithm or something like that. In which case, then you've got a time budget or a computational time budget. So it might be that I'm only going to run 50 iterations through this. Oftentimes, the budget can be in terms of evaluations of F. And this is particularly the case for physical systems, because you might find that if, in order to evaluate F, you have to dump it out into a physical system, then it costs like, $20,000 to run every replication of your physical system, then you have a real dollar budget on how often you can do that. So you really need to come up with a good solution in a certain amount of time. So that's one of the reasons why there are like surrogate optimization methods as well, that as you're evaluating this loop, they're fitting a cheap approximation of your F and then allowing you to, once it's good enough, run a bunch of iterations with this with the cheap version. And only when the cheap version starts to suggest a significant deviation, then it goes back and does a gut check with the real version, the costly one. And if the real version is still in the neighborhood of the cheap version, then it goes back and does the cheap version again. So surrogate optimization methods are simultaneously training approximations and using those approximations as they're trying to optimize the real thing. So that's also going on there, another layer there. So any questions about this? It's pretty much just formalizing what we've been talking about all day today. Okay, so what do we mean by evolutionary then? Let's say evolution. All right. So an evolutionary algorithm is really just an algorithm that uses a population of heuristics, I will say of heuristic optimizers, and reshapes their demographics or distribution. I'll say distribution each step. So, although we're going to be talking about the genetic algorithm, there's nothing genetic about an evolutionary algorithm. An evolutionary algorithm is just something where you start with a population of possible solutions. So you've got an x1 hat or an x1 vector, an x2 vector, an x3 vector, an x4 vector. So these are four different candidates. And for each one of them, you evaluate how well they're doing. And you use then their relative success changes probability of staying in solution pool. So if X1 is so much better than X2, 3, and 4, then it is more likely to stick around. And then if X2, 3, and 4 are really bad, they're very likely to get kicked out. And a new solution, which might be based on X1 or might be totally random, will get substituted in for them. And then that will go on. So it's a way to search multiple. So this here effectively allows for parallel direct searches in the parameter space that communicates, that can communicate. So you might initialize these in very different parameter regions. This is the one that uses is a totally electricity-based solution for powering a nation. This is a totally this well this one this one uses solar power. This one uses wind power. This one uses natural gas. This one uses coal. And so you initialize these four different energy portfolios across your simulation of carbon emissions for the next 100 years or something like that. You go into that simulation, you see how well they do, and then you say, oh, well, this one did a lot better than these, but I'm going to start mixing these together to create alternative portfolios and see how well those do. And that goes on and on and on. And so that's an evolutionary algorithm. It has nothing to do with genes or genetics or anything like that. It just has to do with reshaping populations. And so, these different populations sit in different regions of the parameter space initially. And if it's not like four parallel taboo searches, because they can communicate. And so you don't, if this one's really, really terrible, you just kill it relative to these. If it's not so bad relative to these, you maybe let it go. But if it's really bad relative to these, then maybe you move it closer to one of these so that you get more search power in that area. So that's ways of making them sort of move together. That is a generic evolutionary algorithm. And even things like ant colony optimization, which we'll talk about later, which doesn't use any genetics, which uses the motion of simulated ants through a parameter space, fits this structure. And so, but in which case there it's not even conceptualized as a generation of ants that are dying and having new offspring or something like that. But it still fits this kind of basic structure that every time you go out to find the food, you take a slightly different path, and your path is influenced by how well the other paths have done. And then gradually you converge on the best paths. And that also makes it an evolutionary algorithm. So questions about this general idea? Yeah, on the green. Right. Yeah, so if they're very close to each other, then that creates interesting opportunities. And so sometimes when they're really, really close to each other, we're going to find as we go on here that that actually is not good for our diversity. And so there's something called fitness sharing that we'll learn about, which basically says if all of these are roughly in the same spot, and then I'm actually going to divide their fitness by four. So let's say I have a population size of 20. If these four all are in the better spot of the parameter space relative to everybody else, but they're all crowding there, then I actually penalize them for crowding. And by dividing their fitness by four, then it actually makes it likely that several of these will get redistributed, and then one of them will end up just staying here, and then it will get all the fitness from there. So that helps us make sure that we don't quickly converge on a local optimum and get stuck there. So those are issues, and so we're going to talk about that, in the last few minutes here, and then going into next week on Tuesday, this idea of genetic drift and fixation and the problems it causes, and how genetic algorithms in particular, but to some extent evolutionary algorithms, there's always this balance between what I'll call selection pressure and drift. So between randomness and so random drift, which we'll define, and the pressure to do better. And both of these things purge diversity. And drift is sort of an enemy that you can never get rid of, and it gets worse and worse and worse as you get less and less diversity. So we're always going to battle that. Is like you start out with a huge amount of diversity in your optimization algorithm. You necessarily are going to purge that diversity. And if you're lucky, you end up everybody goes to the best spot in the parameter space. But very often in the intermediate time, you can get a purging of diversity too quickly. And in that case, we need to figure out how to handle that so that we're sure that we're searching through all solutions. And that's what a lot of these intelligent optimization algorithms do. And before you said you also had a question? Mhm. Well, it's sort of up to the algorithm. Most population-based algorithms, evolutionary algorithms that we talk about for computational reasons will replace them. So you just say that I have a vector of optimizers, candidates, and it's a fixed width vector, and so I just need to swap them out. Because if I keep adding to them, then that means that just, now I got to keep, I started with four and now I'm at 40 and now I'm at 4,000. And so at some point, like I just need to stop. And so usually they get replaced. But we're going to talk about these things called elitism, where you'll actually have like a blessed population where if these are really, really good, you save them and sort of guarantee that unless someone definitely beats them out like a lot, you never get rid of them. So you can have two populations, kind of the ones that it's really hard to get rid of and the ones that are easy to get rid of, but still they're usually finite numbers in both cases. Question in the back there? Yeah, go ahead. Yeah, well, I guess maybe to clarify is that um, so like if we think about so F is right now we've got F as a single optimization objective, and it takes we can say multiple scalar inputs. I'll just do three-dimensional here, and I'm going to put a superscript of one above each one of these, and this here I'm calling X superscript one um, vector. And so, and then I would have another evaluation of, let's say, X superscript, this is an X squared, X superscript two, where these together are collectively X2. So this is, and I've swapped, I've gone from subscripts to superscripts here. But the, but the idea here is that the there's only one objective, so there's nothing to weight exactly. And it may be that for this one objective, this dimension is more important than this dimension. So you move in this dimension, it just doesn't change F. But you move in this dimension, and the gradient is very strong, very steep gradient along this dimension, very shallow gradient along this dimension. And so, and we don't know that because we don't have gradient information, but hopefully the search method will figure that out. So it's not there is sort of a intrinsic weighting inside the F function that we don't know about, but that's what we're trying to kind of discover. I wouldn't say that like this one is like it might be that this candidate happens to be its trajectory as the algorithm iterates might be exploring this dimension more than this candidate, but that should be because the optimization algorithm has determined that in this region of the parameter space that maybe this has got the strongest gradient. So we're not quite at weightings yet, but it does get a little confusing, especially once we get to multiple optimization objectives, it'll get even more confusing because we'll have an F1 and an F2. But you've got multiple multivariate candidates, and it's true that some dimensions may be stronger than others, but there's nothing we can do about that. But hopefully the algorithm will figure that out. I don't know if that quite. I'm just sort of throwing out things that I think would help, but did that answer your question, or did I go in the wrong direction? Okay. Initially, usually randomly, same way that you would in like, again, if you've ever trained a neural network, you might choose random weights initially, you might draw them from some distribution. If you have domain knowledge of this particular domain engineering problem, then you might know that, well, typically, like if this is temperature, this is pressure, and this is, I don't know, some other physical variable, then you might know that, well, there's certain constraints that this temperature may can't go lower than X or lower than A and higher than B. But you can say it's typically in our experience good temperatures typically to be around here, and that's where you might initialize that. And so when you're drawing a population of them, then you might say, well, we'll do a bell curve. Like if this is all, we might draw all of these from some distribution which is centered around where the expert said. So our human heuristics have told us that we typically run around there, but we're not quite sure if that's good or not. So you just draw random temperatures around here, allowing yourself to stray, but not straying too far initially, and then let the algorithm stray even further. Other questions? Yeah, I mean, right. I would say that grid cert others that these all fit into these methods. And so this is just providing alternative ways to drive those searches, since that's what we're getting into here. All right. Any other questions about that? The only other thing that I want to mention here that relates to this is the subject of constraints. And so we're going to make this all more concrete next time with population-based examples. But yeah, but you could have for my x vector here, that's broken up into, let's say, you know, x1, and that, may have to come from a certain constrained set, like it can't be any lower than 0 or higher than 5. X2 might have another set of constraints. And then it might be that x3 times x4, those things have to be less than or equal to pi. There could be some weird set of constraints that define the so-called feasible set, which I've been calling X, that where X comes from X. But and so the problem is, how do you stay feasible? Because you're going to be doing a lot of drawing of random one of random candidate solutions. So how to stay feasible? And this is not a trivial problem. And so the easiest thing to do is check feasibility and redraw if necessary. Sorry for the squiggles. Alternatively, you can also project back to feasible set. But this is costly, or can be costly. So what I mean by these things is, let's say that I find out that my candidate solution is bad. Well, I wouldn't need a new candidate solution. I'd like to get rid of this one and put a new one in. I just draw one randomly. Well, randomly, when I draw one, there's a good probability it's not going to meet these conditions. Well, the easiest thing to do is just to, okay, throw it out, draw a new one, throw it out, draw a new one, until eventually I hit one that hits these conditions. That might take a long amount of time. Alternatively, if I do get fall outside of this set, if this set has a kind of boundary which is well defined, I can I can do an alternative optimization problem where I can say, for this little substep, find the of over all of the points in this feasible set, find the nearest one to the one that I drew outside the feasible set. But that optimization problem, hopefully, is just a quadratic or something like that, isn't too hard to solve, but it costs time too. So does it cost more to draw 4 or 5 random numbers, or to project back onto the set? That's going to vary based on how complicated these conditions are. So I don't want to dwell on that, but I do want to say that every real optimization problem is going to have interesting constraints. And so this comes up whenever you do this practically, but I don't have a great solution, but there's a sort of a diversity of solutions that have to be tailored for that particular problem. Most times just redraw and see if that works. And if it doesn't work, then try to find something else. All right, that's all I've got for you today. So we'll see you Tuesday. And then again, Thursday, we've got an alternative instead of lecture.